Hey guys, welcome to our last day of Unit 3. We have made it. I'm so hyped. So, what we're going to do today is we are going to pull everything together, and then we're going to be done with new info for this unit. So, we have two objectives for today, and I'm going to explain why they're super duper important in a moment. But your objectives are that you are going to be able to, you're going to describe London forces, dipole forces, and hydrogen bonds, and then you're going to be able to compare and contrast intermolecular forces. Okay, a lot of words that you don't know yet, but you will by the end of today. Aren't you so lucky? All right, so up until this point, okay, we've been talking a lot about bonding, right? So we've been talking about ionic bonding, covalent bonding, metallic bonding, right? Then we started looking at the shapes of of covalent bonds, right? And then we started looking at polarity and how they can potentially interact with one another. Okay? The bonds that we have been looking at, okay, is what we refer to as intramolecular forces. However, we have another type of force that's important in chemistry and important in bonding called an intermolecular force. All right? So we're going to look at each of them, we're going to break them down, and then we're going to tie it all together. Right? So, intramolecular forces, right? If I hear the word intra, I could think of something such as intramural, okay? Right? These are sports, right? Intramural sports are sports that happen within one school, right? A lot of people, when they go to college, might participate in intramural sports, okay? You might have some here and there, okay? But it's something that happens within one school, okay? So if I have intramolecular forces, right, this prefix intra tells me that it's within one something, right? So intramolecular forces are forces between atoms within one molecule, right? And so we see here in this diagram, in my water molecule, right here we would have an intramolecular force because it's within the molecule itself. Okay. We have different intramolecular forces that we have already learned about. These are all of our bonds. So any type of bond that we've talked about is an intramolecular force, right? We know a covalent bond between oxygen and water, or oxygen and hydrogen that make up water, is held together by an intramolecular force. The ionic bond between Na and Cl are held together by that intramolecular force, okay? Right? We already know, okay, that we have these two types. We know we have an ionic bond, which is between a metal and a nonmetal, okay, or polyatomic ion, depending, right? We know that it gains or loses electrons, it's completely transferred, and that we have polar bonds because they're positive and negative, okay? Covalent bonds, we know, are an attraction between two or more nonmetals, right? We're sharing our electrons, right? And we could be polar or nonpolar. So we're either equal sharing or we're unequal sharing, okay? To make it nonpolar and polar, okay? So all of this stuff you have already learned, okay? We're just putting a giant new name to it as an intramolecular force, okay? And so when I'm looking at my intramolecular force, my strongest is metallic. Okay, my weakest is a nonpolar covalent. Okay, and so as I go down this list, right, I get weaker. Okay, sorry, I just yawned there. Okay, so my strongest is metallic, then ionic, polar covalent, and then nonpolar covalent is my weakest intramolecular force. Okay, so why does this matter? Because not only do my atoms bond together within one atom or within one molecule, each molecule itself can interact with each other depending on their polarity of their overall molecule, right? And how atoms and how molecules interact, okay, are these types of forces. Right? So we saw that when atoms themselves are interacting within a molecule, it's intramolecular force, right? Now if I wanted to look at how they're interacting between each other, I'm looking at intermolecular forces. And we've seen the prefix inter before, right? An interstate highway, okay, is a highway that runs between different states, right? If I took Route 85, Interstate 85, okay, I could get all the way to Washington, D.C., right? Think about an international flight. It's a flight that runs between different countries, right? I could take an international flight from here and go all the way to, I don't know, Greece, right? I'm going between different countries, right? And so intermolecular forces, right, are now attractions that happen between different molecules, right? And so here I'm looking at this dotted line here that shows how this water molecule is now attracting and interacting with this water molecule, okay? And so I have 3 different types of intermolecular forces, okay? I have hydrogen bonding, okay, which is the strongest. I have dipole-dipole, and then I have London dispersion forces, okay, also known as van der Waals. They have like 17 different names. I don't know why. It's kind of annoying, okay? But these dispersion forces are my weakest, all right? So we're going to break down each of them. We're going to give you some examples, and then we're going to do some practice, and then we're done. So when I have hydrogen bonding, okay, this is my intermolecular force that is the strongest, okay? And it's only going to occur between covalent polar molecules, right? So I have to have covalently bonded polar molecules. And we know how to find those polar molecules now because it's based on symmetry. We did this yesterday, right? So our shapes of our molecules that we looked at is now coming together, right? That's why we had to look at it yesterday. Okay, and hydrogen bonding occurs, okay, when a hydrogen of one molecule, okay, right here, right, is going to be, I'm not going to say bonded directly, is attracted. I'm going to change that up. Sorry about that. Okay. Where a hydrogen bond occurs when a hydrogen of one molecule is attracted directly to an atom of F, O, or N from adjacent molecules, right? So this hydrogen here is attracted to an O. This could be an N. This could be an F, okay? If there is no HN, HO, or HF bonds occurring, there's no hydrogen bond, right? So I can only have hydrogen bonding occurring in polar covalent molecules that have these elements, okay? So this is my strongest IMF. This explains why water, okay, is water, okay? This explains why there's surface tension, that capillary action, things that you've learned in biology, right, are now being explained because we now have the knowledge of hydrogen bonds, okay? The next type of intermolecular force is a dipole-dipole bond. And just like hydrogen bonds, it occurs between polar covalent molecules, right? So see this trend, right? I know that it has to be a polar covalent molecule, and we're talking about that symmetry again, right? My unequal symmetry, okay? We know that if I have a polar covalent molecule, I have a dipole, right? So I'm going to have this unequal charge of my positive and negative. And we saw this in the polar covalent molecule lecture, okay? So I'm going to have this dipole happening, the positive and the negative, the partial positive, the partial negative, right? Because they're starting to act like a magnet, but not overall, right? And so what happens is that because of these charges, this unequal sharing of electrons, right, I'm going to have an attraction between my positive end and a negative end, okay? Right? And we see that here, right? We see this negative end of chlorine attracting to the positive end of hydrogen, right? So anytime I have a polar covalent bond that has this dipole interaction here, because all polar covalent molecules will have a dipole, okay, I'm going to have a dipole-dipole force. The biggest difference, though, is it is going to be between molecules that are not HF, HO, or HN, because we know that those are hydrogen bonds, right? So if I have an HS, if I have an HCl, if I have an HBr, I'm going to now have dipole-dipole, right? So it's the same thing as a hydrogen bond, right? Polar covalent molecules attracting the positive and negative ends. The only difference is I don't have these three elements attached to hydrogen, right? So that's why this is dipole-dipole, okay? The last thing to note is the strength of a dipole-dipole depends on how polar the molecule is. So if I'm more polar, I'm going to have a stronger bond. All right. The last type of force we have is a London dispersion force. Okay. This is the weakest of my intermolecular forces because it's going to occur between nonpolar molecules. Okay. So what's going to happen is I'm going to produce like a temporary dipole, right? But my nonpolar molecules really don't have these positive negative charges. They're symmetrical overall, and so they're just going to be attracted to one another by London dispersion forces. Okay, so all nonpolar molecules, when they interact with one another, are going to have this interaction. All right? Okay, so if I look at these examples here, okay, I want to know what type of intermolecular force exists, okay? So if I look here, I have HH attracted to HH, right? I have a non-polar covalent molecule interacting with a non-polar covalent molecule because I know they're covalent because it's all nonmetals, and I know it's non-polar because they're symmetrical on each side. So if I have nonpolar attracting nonpolar, what am I? If you said a dispersion force, you are correct. Congratulations. Okay. Over here, I have polar molecules, and we've already looked at this example 2 slides back, right? I have polar here because they are not symmetrical, right? So I have these temporary positive and negatives, and then I'm attracting each other. So I'm going to have dipole-dipole, okay? The last one I have is NH3, right? If I have NH3 here, okay, I know it's polar because I have a bent shape. And I said anytime I have lone pairs on my central atom, I have a polar molecule, right? And I'm attracting another NH3. When they attract one another, I have N's and H's wanting to attract each other. I know that if it's a polar molecule with N and H, I have a hydrogen bond, all right? So what we are going to do is, okay, oh, before we do that, sorry, right? Copy these in your notes. This is the intramolecular and intermolecular strongest to weakest forces, right? Notice how my intramolekulars are strongest, then go into my intermolecular forces, and each one is completely like stronger or weaker than the one before or after it, right? So I have metallic, ionic, polar, covalent, nonpolar, covalent, then hydrogen, dipole, and dispersion forces, all right? So now, I jumped the gun a little. Here's what I want you to do. I want you to pause this video and I want you to do these practice problems, right? So I want you to identify the intermolecular force that will exist, I should say, between the molecule, okay, right? So the intermolecular force that exists between the molecules, right? So you're going to have to write the Lewis dot structure and then determine the IMF. Aren't you so lucky, right? Once you do that, you're going to write your summary. So you can pause the video, come back when you're done. All right. Okay, I don't know why that just stopped. Now that you are done with your practice, this is your summary task. Answer these 2 questions, right? I don't know why I have adjectives still there. Summary. Okay, what are the London dispersion forces? Or what are London dispersion, dipole-dipole, and hydrogen bonding? How are they different? How are they similar? Once you are done with that, guess what? Independent practice time. Aren't you so lucky?